today's plan is to continue our discussion on three-dimensional kinematics, and I will introduce Euler's theorem. And after that, I will run a very quick review to show you that how the three-dimensional kinematics is related to one-dimensional and two-dimensional kinematics. And with that, you can clearly see the difference of three-dimensional general motion and how we're going to convert angular velocity, displacement, and acceleration to linear velocity, displacement, and acceleration. So that's the plan today. Of course, we'll finish it with an example 31. So that's what we're going to do today. For those of you who needs to know which part the derivation for three-dimensional kinematics is on my notes, page 57 to page 58. So you can just go back there. Now, what is Euler's theorem? Well, but first of all, we have to be careful here. Why? Because you're dealing with one of the most productive scientists or scholar in the history of mankind. This person, Euler, he has so many theories that it is absolutely unclear that which theory is this one about. So just keep in mind that you're going to see many of this name again in your career. So who is Euler? Euler is Leonhard Euler, and born in April. We just passed his birthday. April 15, 1707. He passed away on September 18, 1783. He was a Swiss mathematician, but he spent most of his time and his career in Russia, in St. Petersburg. So Leonhard Euler has something to do with civil engineering, because today we also have, this is what we call Euler, Bernoulli beam theory. And Bernoulli, of course, this is actually another puzzle that civil engineers will sometimes can be confused by this name, Bernoulli, because there are so many good Bernoullis. There's a Daniel Bernoulli, there's a Johann Bernoulli, there's a Jacob Bernoulli. Jacob Bernoulli was a famous mathematician in probability. Daniel Bernoulli was actually a civil engineer. He had great contributions in hydraulics and fluid mechanics. If you are taking fluid mechanics, you're going to see his name again. So this Bernoulli is Daniel Bernoulli. And Daniel Bernoulli and Leonhard Euler proposed the following theory, and this is what we call the Euler-Bernoulli beam theory, which is essentially to relate deflection to loading. Suppose you have this loading denoted by W, and your deflection is X, something like that. So what I found is this: EI to the fourth order of, actually X is measured in this direction. This is the X direction, and this is W direction. So this is X, and deflection here is Y. So this is what you have. If you differentiate the loading 4 times with respect to the X-axis, you're going to get deflection. The loading and deflection are related by this relationship. So this is what we call today Euler-Bernoulli beam theory. And you're going to see many of them from strength of material, structure analysis, same thing with mechanical engineering students. What is Euler's theory? Euler's theory is about this. Suppose you have an object, and this object is under not just uniaxial rotation, but triaxial rotation. Triaxial rotation certainly can be described by what? By multiple components of angular velocities or acceleration. Now remember, we usually define motion by velocity, not necessarily by acceleration. This is an important concept that after this dynamics, you must understand that motion, especially relative motion, is usually described by velocity. So velocity is actually perhaps the most important parameter out of displacement, velocity, and acceleration. Because even right now, we are still standing. You're sitting at home, and you probably don't feel any motion because we are in constant acceleration motion. Why constant acceleration motion? We don't feel the spinning of Earth, right? And yet we are moving. So when acceleration is constant, also is not zero, you still do not feel motion. However, when velocity is not zero, you will definitely feel motion. Therefore, dynamic behaviors can be best described by the non-zero velocity, not acceleration, but velocity. So we're going to describe this by velocities. And by this right-hand rule, this is like this. We're going to say this is omega 1, omega 2. Suppose we consider 2. Of course, you can even describe it by 3. You say, I would like to have another one. I'm going to call this one omega 3. And here, if x, y, z is like this, actually, I'm going to call this one x, this one y, and this one z. Not in particular order, but just for following the right-hand rule. Okay. So what Euler says is this. Compared to just the uniaxial motion or angular motion, in which you only have one angular velocity to consider, and the conversion between linear and angular parameters. It's very straightforward. We already talked about it. But what if you have an object is not only spinning in one direction, in the meantime, it's also spinning in other directions. So how do we figure that out? Now be careful that in this case, you're going to get this superposition is not that straightforward. Some may say that, can I just consider the angular motion here first, and then I consider this one? No, you cannot. Why? Just think about that you're trying to spin something. Okay? Maybe at the end of the motion, just think about in time domain. In time domain, if I want to consider the spinning of this ball, this point, which is back to this angular motion, like this, and this ball, A. So the path of this ball, this point A, in time, will look like something like this. It's going like a sine, right? Because the ball is spinning and A is going to go round and round like this, which is back to the time axis. Of course, we also consider that this is how the point A is going to spin like this. But if this ball with the point A located right here is subjected to also another motion, another angular motion with respect to here, and you know that it's certainly going to destroy this path. It's not going to be like this. So you cannot simply just consider that the combination of these two is directly linear for a long period of time. Even at the end of the time, maybe they will give you the same result, but during the motion, between 0 to any time in between. So this is actually the motion caused by this omega 1. And suppose it's another omega 2. Now let's look at how this in time domain. Suppose this is the motion of A with respect to the omega 2. And that's caused by this red omega 2 angular velocity. So how would the point A, what is its path? How does the path look like in time?
Just a straight line?
Yes, because if you define everything here, right, it's just a straight line like this. So it's going to look like just a straight line.